All right, welcome to another deep dive, everyone. So you're knee-deep in circuit analysis, huh? I bet you've got a mountain of textbooks and notes staring back at you right now.
And you know what? We're about to climb that mountain together and uncover the secrets of simplifying resistive circuits.
You got it. Today, we're all about streamlining your analysis, giving you the tools to look at a messy circuit and see the elegant simplicity underneath.
Because let's face it, when those circuits start to sprawl and you're trying to wrangle them with just Kirchhoff's laws, well, you can end up drowning in a sea of equations.
Exactly. Imagine a network of resistors and sources all tangled up, and you're trying to solve for currents and voltages using those fundamental laws directly. It's like trying to untangle a giant knot.
Yeah, absolutely. It can get really messy really quickly, but that's where the beauty of simplification techniques comes in.
Exactly. We're going to break down 3 powerful methods that'll make your life a whole lot easier.
We'll start with source transformations, a really clever way to shift between voltage and current source representations. It's like having different perspectives on the same problem, giving you the flexibility to choose the view that makes the solution clearer.
Then we'll dive into Thevenin and Norton equivalents, which are amazing for condensing a whole chunk of a circuit into a single source and resistor combination.
Think of it like this. You can take a complicated network and boil it down to a simple battery and resistor model.
And finally, we'll explore superposition, a technique for analyzing circuits with multiple independent sources by breaking down the problem into smaller, more manageable pieces.
It's a divide and conquer strategy that helps you untangle the contributions of each source individually.
All right, let's jump right in with source transformations. Now, this technique is mentioned in your materials as one of the key ways to simplify circuits.
Yeah, and it's often presented alongside those other simplification methods you might have seen, like combining resistors in series or parallel, or those things called Y to delta transformations.
Right, right. All those handy tools for redrawing and simplifying circuits. So at its heart, what a source transformation lets you do is take a voltage source, the kind that's in series with a resistor, and swap it out for a current source in parallel with that same resistor.
The key here is that under the right conditions, these two setups, the voltage source with a series resistor or the current source with a parallel resistor, become electrically equivalent.
So it's like two sides of the same coin, electrically speaking.
Exactly. And the crucial part is, this transformation works both ways. You can go from voltage source to current source, or from current source back to voltage source, as long as you follow the rules.
Okay, so what are these magical conditions that make this swap possible? How can we be sure these two configurations are truly behaving the same way?
Well, the fundamental condition for equivalence is this. The current flowing through any resistor that you connect to those terminals must be the same in both configurations.
So it doesn't matter if I'm looking at the voltage source setup or the current source setup, the impact on any connected resistor is identical.
Precisely. That's the key to this whole transformation. Ensuring that the external behavior, how the circuit interacts with anything connected to those terminals, remains unchanged.
Got it. So the impact on the outside world stays the same, even though we've changed things internally. So how do we actually make the switch? Is there like a formula or something for this?
Oh, there definitely is.
Yeah.
Let's say you've got a voltage source, we'll call it V's, and it's in series with a resistance, we'll call that R. You can transform this into a current source, we'll call that is, and the value of that current source is just V's divided by R.
Okay, so is equals V's over R, simple enough. And this current source is would be in parallel with that same resistance R, right?
That's it. You've got it. And this equation is your key to making these source transformations work for you.
Now, what about the direction of that current source is and the polarity of the voltage source, V's? Do those matter?
They absolutely do. If you reverse the polarity of that original voltage source, you have to flip the direction of that equivalent current source too. This makes sure everything stays consistent, like the direction of energy flow.
Right, so we're not just playing around with numbers here. It's all about maintaining the fundamental electrical relationships within the circuit, keeping everything balanced.
Exactly. Now, you might be wondering, why does this even work?
Yeah.
What's the logic behind this whole transformation?
Yeah, I was just going to ask that. It seems almost like magic.
Well, it's not magic, though. It can feel that way sometimes. Think about it this way. If you connect a resistor to those terminals with the voltage source and series resistor setup, the current flowing through it depends on the total voltage and the total resistance, right? This good old Ohm's law for you.
Right. Voltage equals current times resistance. Classic.
Now, if you connect that same resistor to the current source and parallel resistor setup, you have to think about current division. It's all about how that total current from the source splits up between those parallel paths.
Ah, I see where you're going with this.
For the currents through that connected resistor to be the same in both cases, that relationship is equals V's over R has to hold true. It's like Ohm's law and current division working together behind the scenes to ensure that everything matches up perfectly, to maintain that external equivalence.
Okay, that makes a lot more sense now. So it's not just about blindly swapping components. There's a real elegance to this, like a hidden harmony in the circuit.
Absolutely. Now, your materials actually have a great example of this in action, right?
Yep, there's one that walks through finding the power associated with a 6-volt source in a circuit.
Ah, yes, I remember that one. It starts by transforming a 40-volt source with a 5-ohm resistor, and it takes you step by step through the process so you can see exactly how it works in practice.
Right, so first they use that source transformation, turning that 40-volt source with a 5-ohm resistor into a current source.
Exactly, and that current source would have a value of, well, let's see, 40 volts divided by 5 ohms, that's 8 amps, right?
Yep, 8 amps. And that would be in parallel with that 5-ohm resistor.
Precisely. And once you have that current source in parallel, you might find other resistors in the circuit that are also in parallel with it.
Right, right. And then you can combine those parallel resistances into a single equivalent resistance, making the circuit a little tidier.
Exactly. And then, depending on what you're trying to solve for, you might want to transform that current source back into a voltage source.
Why would you want to switch back?
Well, sometimes it makes the analysis easier. Like if you need to combine it with other series elements, or if it just simplifies applying Kirchhoff's voltage law.
Ah, so it's all about strategically choosing the representation that makes the problem flow more smoothly.
Exactly. And in that example, after switching back to a voltage source, they combine some series resistors and then do one final transformation to find the current through that 6-volt source.
And then they calculate the power and figure out if it's being absorbed or delivered by that source.
Exactly. And that example really highlights how powerful source transformations can be. By applying them strategically, you can often take a messy circuit and break it down into something much simpler, making those final calculations a breeze.
Now, there was one thing that kind of tripped me up when I was reading through the material. It talked about what happens if you have a parallel resistance with a voltage source or a series resistance with a current source. And it said that those extra resistances have no effect on the equivalent circuit, at least not with respect to those terminals. That seemed a bit strange to me.
Yeah, I can see why that would be counterintuitive at first. But think about it this way. An ideal voltage source, well, it's supposed to maintain a constant voltage across its terminals, no matter how much current is flowing through it.
Right, right. That's the ideal scenario, at least.
So if you stick a resistor in parallel with that voltage source, it's going to have that same constant voltage across it, regardless of what else is going on in the circuit. That parallel resistor is kind of doing its own thing, drawing its own current, but it's not really changing the voltage that the source is providing at those terminals. It's like adding a side path that doesn't affect the main flow.
Okay, I'm starting to see it. So that extra parallel resistance is there, but it's not messing with the fundamental voltage at the terminals.
Exactly. And the same logic applies to an ideal current source with a series resistor. That current source is pumping out a constant current, no matter the voltage across it. So that series resistor will just drop some voltage based on that constant current, but it won't change the amount of current that the source is delivering to the rest of the circuit.
Ah, got it. It's like that series resistor is just along for the ride, but it's not messing with the current flow.
Precisely. So these extra resistances, they're there, but they don't really affect the behavior of the source as seen from those terminals. It's all about remembering the core properties of ideal voltage and current sources.
All right, that clears things up. So source transformations, pretty neat trick, huh?
Absolutely. A great addition to your circuit analysis toolkit.
So let's move on to part 2, Thevenin and Norton equivalents. It sounds like these take simplification to a whole new level.
They really do. Imagine being able to take any linear resistive circuit, no matter how complex, and replace it with a simple equivalent circuit, just from the perspective of a specific pair of terminals.
So you're saying we can take a black box circuit with all sorts of craziness going on inside and boil it down to something much simpler.
Exactly. And it all comes down to understanding how that circuit behaves at those terminals. It's like creating a simplified model that captures the essence of the circuit's interaction with the outside world.
Okay, let's start with the Thevenin equivalent. What exactly is it?
A Thevenin equivalent is a representation of that complex circuit using just two components. an independent voltage source, which we call VT8 for Thevenin voltage, in series with a resistor, which we call RT8 for Thevenin resistance. And the amazing thing is, this simple two-component circuit can behave exactly like the original complex circuit, at least as far as anything connected to those terminals is concerned.
Wow, so if I hook up a load to those terminals, it won't know the difference whether it's connected to the original circuit or to this simplified Thevenin equivalent.
Exactly. That's the beauty of it. The Thevenin equivalent captures the essence of the original circuit's behavior at those terminals, no matter what kind of load you connect.
That's pretty impressive. So how do we actually find these two magic values, the Thevenin voltage VT8 and the Thevenin resistance RT8?
Well, finding VT is actually pretty straightforward. You simply calculate the open circuit voltage at the terminals of interest in your original circuit.
Open circuit voltage meaning?
Meaning, you measure the voltage across those terminals when nothing is connected to them. You're essentially seeing what the circuit wants to do when it's left alone, what voltage it naturally settles at those terminals.
Ah, okay, so that open circuit voltage is our VTH. Got it. What about the Thevenin resistance, RTH? That sounds a bit trickier.
There are a couple of ways to find RTH. One common method is to calculate the short circuit current at those same terminals in the original circuit. We'll call that ISC.
The short circuit meaning we.
Meaning you connect a wire directly across those terminals, essentially creating a path of zero resistance. This forces the maximum current the circuit can provide to flow through that short circuit.
Okay, so we find the open circuit voltage, VT8, and then we find the short circuit current, ISC. And then what?
Then it's simple. The Thevenin resistance, RTH, is just the ratio of those two values, VT divided by ISC.
Interesting. So the open circuit voltage and the short circuit current are directly related to this equivalent resistance. It's like they contain the information we need to find RTH.
Exactly. They're like two sides of the same coin, revealing different aspects of the circuit's internal behavior.
Now, is that the only way to find RTS?
Nope. There's another method that's especially handy when your circuit only has independent sources, no dependent sources to complicate things.
Okay, those independent sources, they're the ones that just do their own thing, right? Their values aren't affected by anything else going on in the circuit.
That's right. So in this case, to find RTS, you first deactivate all those independent sources. And by deactivate, I mean you replace voltage sources with short circuits and current sources with open circuits. Essentially, you're turning off those sources and seeing what's left behind.
Okay, so we turn off the sources, and then what?
Then you simply calculate the equivalent resistance looking into the terminals of interest. It's like peering into the circuit from those terminals and figuring out what resistance you see looking back in. The resistance is your RTS.
Got it. So we're finding the passive resistance of the network, the resistance that's always there, even when the sources are off.
Exactly. It's like stripping away the active parts of the circuit and seeing the underlying resistance structure.
Now, the material mentioned a third method for finding RTS, specifically for circuits with dependent sources.
Ah, yes, dependent sources. Those can be a bit trickier to handle because their values depend on voltages or currents elsewhere in the circuit. You can't just deactivate them like independent sources, or you'll lose that crucial dependence.
So it's like they're influenced by the rest of the circuit, making things more complicated.
Exactly.
Yeah.
For dependent sources, one common approach is to deactivate all the independent sources, like before, but then apply a test source at the terminals of interest.
A test source.
Yep, you basically introduce either a test voltage source or a test current source at those terminals, and then you measure the resulting current or voltage caused by that test source.
So it's like we're probing the circuit with a known signal to see how it responds.
Precisely. And then you can use those measurements to calculate RTS. It's a bit more involved than the other methods, but it's a reliable way to handle those tricky dependent sources.
Got it. So we've got our three ways to find RT, depending on the type of circuit we're dealing with. Now, the material also had an example where they calculated both the open circuit voltage and the short circuit current to find a Thevenin equivalent.
Right, that example shows you the step-by-step process. First, you analyze the circuit with those terminals open, no load connected, to find VT8. Then you analyze it again with the terminals shorted together to find ISC. And finally, you divide VT by ISC to get that Thevenin resistance, RTH. Boom, you've got your Thevenin equivalent circuit.
Okay, now there was this other thing mentioned, the Norton equivalent. How is that related to the Thevenin equivalent?
The Norton equivalent is like the Thevenin equivalent's twin brother.
Twin brother. So they're very similar.
Oh, they're practically the same thing, just expressed in a slightly different way. Instead of a voltage source in series with a resistor, the Norton equivalent uses a current source in parallel with the resistor.
So it's like flipping the script, going from voltage to current. And how do we find those values for the Norton equivalent, the Norton current, and the Norton resistance?
Well, the Norton current, which we call IN, is actually equal to that short circuit current, ISC, that we use to find the Thevenin resistance.
Ah, so we've already calculated that.
Exactly. And the Norton resistance, RN, is simply equal to the Thevenin resistance, RTH.
So really, the Thevenin and Norton equivalents are two sides of the same coin.
Exactly. You can actually transform a Thevenin equivalent into a Norton equivalent using a source transformation, and vice versa.
Wait, so that source transformation trick we talked about earlier, we can use that to switch between Thevenin and Norton equivalents too.
Absolutely. It's all connected.
Okay, my mind is officially blown. Now, the material mentioned that sometimes you can use source transformations to directly derive Thevenin or Norton equivalents, but it seems like dependent sources can make that a bit tricky.
You got it. With independent sources, it can often be pretty straightforward. You just keep applying those source transformations, simplifying the circuit step by step until you're left with a single source and resistor at those terminals.
And boom, you've got your equivalent circuit.
Exactly. But with dependent sources, you have to be careful because you need to preserve those controlling voltages or currents. You can't just eliminate them during those transformations or you'll mess up the circuit's behavior.
Right, those dependent sources are a bit more delicate, a bit more sensitive to changes in the circuit.
Exactly. And that's why the test source method for finding RTA is so useful, especially when you have those dependent sources. It gives you a reliable way to find the equivalent resistance without worrying about accidentally changing the circuit's behavior.
Okay, so source transformations, Thevenin and Norton equivalents, it's all starting to come together now.
It's all about simplification, about finding those powerful tools that let you analyze complex circuits without getting lost in the complexity.
Okay, let's tackle the last part of our deep dive today. Superposition. It sounds like this is the technique to use when you have multiple sources in a circuit.
You got it. Superposition is a lifesaver when you're dealing with linear circuits that have more than one independent source.
Linear circuits meaning?
Meaning circuits where the components behave nicely, where the relationships between voltage and current are linear. No weird nonlinear stuff going on.
Right. So resistors, capacitors, inductors, those kinds of components.
Exactly. And the beauty of superposition is that it lets you analyze the circuit as if each source were acting alone. You break the problem down into smaller, easier to manage pieces.
So if I have a circuit with, say, a voltage source and a current source, I can analyze it twice, once with just the voltage source doing its thing and once with just the current source active, and then I can just combine the results.
That's the gist of it. You analyze the circuit for each independent source individually, as if it were the only source present, and then you add up the results to find the total response.
So it's like we're isolating the contribution of each source and then combining those contributions to get the complete picture.
Exactly. And when you're analyzing the circuit for each individual source, you deactivate all the other independent sources.
Deactivate meaning?
Meaning, you replace voltage sources with short circuits and current sources with open circuits. It's like turning off those other sources while you focus on one at a time.
Okay, so we turn off all but one source, analyze the circuit, then do the same for the next source, and so on. And then we just add up all the individual responses.
Yep, you add them up, being careful to pay attention to the directions of currents and polarities of voltages. It's all about combining those individual responses correctly to get the total response of the circuit with all the sources active.
Now, the material had an example with a circuit that had both a voltage source and a current source, and they used superposition to find the branch currents. It was really helpful to see how it all works in practice.
Right, that example walks you through the steps. They find the currents due to the voltage source alone, then the currents due to the current source alone, and finally, they add up those corresponding currents to get the total currents in each branch.
Okay, that makes sense. Now, there was this one really important point about dependent sources and superposition.
Yes. You have to remember that dependent sources are never deactivated when you're applying superposition.
Never. Why not?
Because they're dependent, remember. Their values are tied to other voltages or currents in the circuit. If you deactivate them, you break that dependency and change the whole behavior of the circuit. You lose that controlling influence.
Right. So those dependent sources have to stay active even when we're focusing on individual independent sources.
Exactly. They're still part of the circuit, and their values will be affected by the active independent source. So they need to be included in the analysis for each individual source.
Got it. So it's like they're always listening to what's going on in the circuit, even when we're pretending that only one source is active.
Precisely. And the material even has an example with both independent and dependent sources, showing how those dependent sources are left alone while you analyze the circuit for each independent source separately. It's a good reminder to treat them differently from those independent sources.
All right, so we've covered source transformations, Thevenin and Norton equivalents, and superposition. That's a lot of simplification power.
It really is. And these techniques are essential for anyone tackling circuit analysis. They give you a way to look beyond the initial complexity and see the underlying structure and behavior of circuits.
So next time you're staring at a circuit that looks like a tangled mess of wires and components, remember these tools.
Don't panic, you've got this. Use source transformations to shift your perspective, find those Thevenin and Norton equivalents to condense things down, and apply superposition to break down those multi-source problems.
It's all about choosing the right approach, the right tool for the job.
Exactly. And with practice, you'll develop the intuition to know which technique will work best for different situations.
So to all those out there battling their way through circuit analysis, we hope this deep dive has given you some new weapons in your arsenal.
And remember, circuit analysis isn't just about solving equations. It's about understanding the flow of energy, the interactions between components, and the elegant simplicity that can emerge from apparent complexity.
Thanks for joining us on this deep dive.
See you next time.